next presentation, I was going to read this very long bio of our presenter, but as you heard in the keynote this morning, I think Jeff did a good job of giving his full background. So literally, Pete is a rock star in AI and specifically in TensorFlow Lite. And with that, Pete Warden.
Thanks so much. Yeah, I'll shake hands. So I have a little prototype in my hands here. So this is really good to be here. Thanks so much for attending. There's always a really good audience at these Embedded Vision Summit talks. And this morning, I was giving a very, very high-level view of where I think we're going. What I'm going to be doing in this session is actually trying to talk about some of the nuts and bolts of how you can actually use TensorFlow now to do machine learning on really low power devices. And the first thing that I'm actually going to do is give a quick demo. And what I'm going to do is, this is a SparkFun Edge board, which is a small Ambic Cortex-M4 CPU that is using roughly on the order of about a milliwatt of power. And it's continuously running a speech wake word demo application that we have open sourced. And luckily for this demo, you can't actually see the LEDs because they're too small. But you'll have to take my word for it. When I shout yes, it actually lights up some of the LEDs because it's recognized the word that I'm saying. I'm actually going to pass this around the room. Hopefully, not too many of you will need to shout yes, though that always helps my affirmation as I'm going through the talk, having just so you can actually have a play with it yourself. And I really wanted to start off with that demo just to show you that this is not just some sort of head in the clouds fantasy. There's real practical coding and real practical applications that you can start building with TensorFlow Lite for microcontrollers right now. And I'm going to take my life in my hands by seeing if I can actually Alt-Tab to something that's actually showing code. So let's see if we can just go to, and really just what I wanted to show you here is that whole demo, that's in the GitHub open source for TensorFlow. And it boils down to a comparatively small number of C++ lines where we're grabbing audio data, we're creating spectrograms from that audio data, and then we're calling invoke on the interpreter that contains a model. And that is actually running the speech recognition neural network on the spectrograms. And the spectrograms in the image world, they're effectively small one-channel images showing the frequencies over time of some audio data. So we're actually using a 20 kilobyte image recognition style neural network in this case. And then we're just taking the outputs and sort of averaging them. And if we find the yes command was recognized, we'll light up the LEDs. Oh my, it actually worked. So what was that? It's a wake word recognition example running on an ARM Cortex-M4 chip, in this case from Ambic. And Ambic has a special process that lets us run that chip with just a very like 1 or 2 milliwatts power usage. So it can run on a coin battery for days. And this demo is completely open source. And what I'm going to do for the rest of this talk is actually show you how to build it. Before I show you how to build it, what is TensorFlow Lite? A lot of people have run across TensorFlow. It's our open source project within Google designed to bring machine learning to everyone. And it works well on server-side devices. But TensorFlow Lite was designed because we had a whole bunch of things, especially phones, where you couldn't afford the megabytes and megabytes of program data that you needed to run full TensorFlow. So running on smartphones and things like the Raspberry Pi, you can only fit hundreds of kilobytes. So that is what TensorFlow Lite was designed for, as a companion project to take TensorFlow models and especially run inference on them efficiently within a much smaller footprint. And it's now on over 2 billion mobile devices out there in the world. So that was great, but what we found was there were a lot of people who wanted to build products and build applications that ran on things that were even smaller than mobile phones. And if we want to run on these embedded devices, on these MCUs, we need to run within like tens of kilobytes, like low tens of kilobytes of code footprint. There's probably going to be no operating system. You can't rely on having an operating system there. You can't do malloc and free. So what we set out to do was say, hey, we want to keep all of the nice things about TensorFlow Lite, like the tooling, the API, the documentation, the examples, but we don't want the bulk that you get from having the all of these dependencies and all these things that are hard to support on microcontrollers. So we managed to create a version of TensorFlow Lite that actually meets these constraints and will fit into just a 20 kilobyte code footprint. So that's really what TensorFlow Lite for microcontrollers is all about. And why am I talking about a voice example at an image conference? Well, the voice example really is the hello world of running embedded machine learning. It's the most common use case for running machine learning on DSPs and other kinds of microcontrollers right now. So we knew if we were going to be successful, we had to support that use case as kind of our foundation. But as I mentioned, it's actually using image recognition internally on a spectrogram. So it's already starting to apply to, you're starting to use vision techniques. And we are looking at working actively on getting more examples out. The very next example we're working on is getting a vision recognition example. And the main bottleneck there is that we're actually trying to get the hardware put together so that you can actually have a sub 1 milliwatt camera running. And as it's part of TensorFlow Lite, that means that as we're building out TensorFlow Lite for microcontrollers, you're going to get automatic access to a lot of the models that are supported through TensorFlow. So I'm going to talk through this tutorial a bit. Now, I'm not expecting you to memorize everything that I'm saying here. I really am hoping that this will act as kind of a companion to people who are looking at the tutorial itself. And there is a code lab at this link that you'll see up there. But I want to sort of give you the the director's cut, the director's, I guess, the DVD commentary on top of the tutorial. So one of the things that's probably going to be most daunting as a embedded developer is most machine learning expects you to be very comfortable and familiar with tools like Python, especially, and working on Linux, and generally have a high degree of comfort with these server-side, these desktop kinds of interpreted languages and tools. We know that that's going to be a barrier for a lot of people, so the tutorial includes a link to a precompiled model that you can just download that has trained for just the yes-no wake word recognition that we have running on that device. But we also have a one-line script that you can run to train the model yourself from open source data. So the first thing I want to say is, like, if you're working on a Windows machine and you really don't want to deal with like all of the pain of trying to learn machine learning concepts on the model creation side, don't worry too much about that. You can use the examples we have with TensorFlow Lite without having to worry about training at all. And we also spend a lot of time actually trying to put together examples where you can do things like transfer learning, which is a way of actually taking pre-trained models and just retraining the very final layer, which reduces the amount of work you have to do training. It also reduces the amount of data that you need to retrain a new model. So if you're interested in taking a sort of a baby step towards training, if you look up TensorFlow for Poets, that is actually an example of training a image model for TensorFlow Lite that you can just train with just a few images in your own image folders and actually get pretty good results. So another big challenge we faced when putting together the example was almost no boards actually ship with microphones. Almost no microcontroller embedded development boards came with microphones. We did actually find the STM32 F746NG. I love the naming in the embedded world. Discovery board, which does have, it's quite a high-end processor. It's like an M7, but it does have a couple of microphones built in and some embed libraries for actually accessing those microphones, which is equally important. And we do have some examples for running on embed, if that is the platform that you're more comfortable with. And we also have some support for projects in Kyle as well. So we have tried to go to the sort of IDEs that people are actually comfortable with. We aim, our default, because it's Google, is everyone's running on a Linux desktop machine, and we're using open source tools like GCC. So as I mentioned, we have support for other sorts of environments too. We actually also have some experimental Arduino library support, which we're working on. But if you just want to kind of get started, the simplest way that we recommend is using the source code that's in GitHub and actually running it on some kind of Linux machine. Now that Windows actually has the Linux kernel support built in, I'm hoping that it will get even easier. There's some magic in actually setting up binaries for this SparkFun board that's being passed around, because what we're effectively doing is using a serial connection to kind of do an over-the-air update. And the bootloader on that device has a whole bunch of smarts to make sure that you've actually got kind of a signed over-the-air update. So the actual building of the code itself is a one-line make command, and it should only take sort of 30 seconds to pull all of that together. But then you actually end up running some scripts to actually do the signing of this binary in preparation for sending it over the UART, sending it over the serial connection from your host machine to the main computer, to the main microcontroller. Another thing that I've had a lot of fun with is, you can probably see from this diagram, it's not the most kind of robust connection, mechanically speaking. trying to attach a serial breakout board to the development board and then attaching your USB controller to that. And after you've actually got that working, even sort of mechanically, there's also a bunch of stuff, depending on your system, that you need to do to actually get the UART showing up. You have to mess around with /dev to make sure that there's actually a TTY console showing up. It's probably one of the most common places to hit bugs. There's GitHub issues on some of these questions, but also feel free to email me at petewarden, PETEWARDEN, @google.com to let me know when you've actually filed bugs, because even I've had some trouble on new machines getting all of the serial port stuff set up in this case. Then, I always think of this as kind of like a Vulcan nerve pinch. You end up having to run a script, hold a button just as you're running the script, and then press another button, and then run the script, and then like let go of the reset. So this is one reason why I really want to actually, well, first off, I'm hoping that in future revisions of the hardware, we'll make this easier. Some of you as embedded software developers, you may think that this is just kind of par for the course. As somebody from the more delicate world of server-side development and mobile development, this kind of blows my mind that we need to do things like this. And I also, this is one of the places where I'm hoping that we can actually put together some more sort of video and some more annotated examples around how to actually get this going, because this is the sort of thing that is a genuine barrier to entry to a lot of people just getting this working. If you get this far and you aren't able to actually get the special button command working, then you're going to be very disappointed. So almost none of what I was talking about there was about touching the code itself. We've tried to set it up so it does something useful by default, lighting up the LEDs. And this is the actual code itself that is, because we don't have string comparison in the bare metal setup that we have here, we're just using kind of the first letter of the string that's returned from the speech recognition model to light up different LEDs. But really the goal here is that once you've got all of this working, you can actually start to have the device kind of respond to things in different ways. You can actually have actuators do something, and also go back to the training step and start training this for kind of noises that you actually want it to respond to. So actually doing retraining, one of the requests we've had a lot is like, hey, can we have this retrained on like breaking glass, so that it sits there listening and it actually lights up, and sends off a radio command or something like that if it hears something like breaking glass. So we're hoping that this is going to be a fun kind of stepping stone project for anything that you want to do that's looking at time series data, including things like predictive maintenance. We've had some promising results where people have actually trained, instead of microphone data, on accelerometer data that's coming in through machinery and through bearings, and is actually able to tell when a bearing is getting worn using almost exactly the same code that's being run in this example. So, like I said, I don't actually expect you to have absorbed everything that I'm saying. I'm hoping that I've given you enough hints that when you sit down with the tutorial and with the code lab itself, you won't be taken too by surprise, and some of the areas that are particularly tricky will actually be a little bit easier. We do have all of this code, along with a bunch of documentation, up on GitHub. We welcome GitHub issues. We actually welcome ideas on extending this. We are working on more examples ourselves. We would love to see code contributions from the community as well. And as I mentioned, I'm really keen. Like, this is a really innovative and extremely skilled audience, which is why I'm excited to be speaking to you this afternoon. So please do email me with your questions, with requests, and let me know how we can help build really cool stuff together. So I think that's it for my main talk. And
Thank you, Pete. So if you have questions for Pete, please step up to the mic. Very good.
Hi, great showing us all the warts, so it would be easier. With the TensorFlow Lite, if you have a model that you've trained with the other TensorFlow, is it something that you can then easily import, or is that the idea from it? I mean, the code that you have
yes,
portable or somehow?
Exactly. TensorFlow Lite is designed to be, a companion project with basically its sole purpose is to take TensorFlow models and run them. So the export process is not always as easy as we'd like, but mostly because the training environment is so different than the inference environment. Like, we often need to get rid of particular operations that make sense during training but don't make sense when you're actually deploying. Like things like batch normalization, you want to kind of like fold that in so you're not doing the full batch normalization operation every time because it's constant. And yes, it should work with a wide range of TensorFlow models. It's probably the area that's one of the areas that's easiest to get kind of stuck with. So that's an area where we keep working on the tooling. Thanks.
Do we have any other questions for Pete?
And if you let me know where the SparkFun Edge board ended up.
We got another question.
Oh, is there another question?
Yeah. He's walking up to the mic.
Oh, awesome.
Thanks, Pete. I enjoyed both your keynote this morning and this presentation. Very exciting and very inspiring, especially your keynote message was very inspiring. I have a couple of questions, actually. We are using TensorFlow Lite, TensorFlow 1 point whatever, right?
Yeah.
1.12 actually, but it's not that important. The question is, moving to TensorFlow 2.0, will we have to change our inference application, which is written in C++ using TensorFlow Lite 1.12? Will we have to change our application if we move the application code, if we move the inference application to use TensorFlow Lite 2.0? Obviously, we will have to relink our application, but do we have to change our code?
So the goal is that you should not have to change your code. I believe that you should just be able to relink and rebuild, and most things should just continue to work. Now, that's barring bugs, and 2.0 is still in its alpha, so it's still still fairly bleeding edge. But yeah, the goal is to keep kind of API stability and like keep things that are working.
And when is the official release expected? 2.0?
I'm actually completely out of the loop on that. I've been so focused on the microcontroller.
Well, speaking of the microcontroller, you provided the example of voice recognition using TensorFlow Lite for micro. Is there any anything that could prevent just to build TensorFlow Lite for micro and use it for purely image recognition or classification application?
So it's still, we're still building some of the system level building blocks. One of the big challenges we face is that because we're working in a system, we can't assume that there's malloc and dynamic memory allocation. We're actually having to rewrite the activation layer allocator so that it takes a fixed size arena. We're hoping to have that done over the next couple of months, or sorry, over the next couple of weeks, actually. We have some code changes under review right now. And that should actually let us run MobileNet. So we're looking at 250 kilobyte-ish mobile nets that we're putting together to do especially person detection, like is there a person in this image? And you should be able to go ahead and run those. Now, we also don't have full TensorFlow Lite op coverage in micro yet. So if you're running, like we're working on that over the next few months, but if you're taking TensorFlow Lite for microcontrollers right now, you might find that one of the ops that you're using is not supported. So it's still a fairly bleeding edge project itself. But I'm hoping that with a bit of help from our side, you should be able to get things that you want to do up and running.
Thanks so much.
No problem.
Thank you. Any other questions for Pete? Okay.
Your talk was focused on this microcontroller. I'm wondering how broad is the support for all of the microcontrollers and all of the platforms above the microcontrollers, and how does that ecosystem develop, and what does that look like?
No, that's a good question. Really, one of the things that I firmly believe is that this neural network, the core neural network operations are just math, and they should be the most portable thing in the world. So what we've tried to do is write a very, very small, hopefully easy to understand, easy to compile set of code to run the neural networks correctly and have it be very, very portable to a lot of different platforms. So we have had it running on a whole bunch of different architectures. And I'm hoping it continues to stay, like we're planning on having it continue to stay very, very portable so that you can, like for example, if you want, we're hoping you can take like the individual op implementations and kind of like use them within like other code bases or, kind of pick and mix pieces and help compose systems and things like that.
Is that going to happen at the developer level, or are the chip companies going to support that, or is it everybody?
So what I'm really hoping is that we're getting a lot of contributions from chip companies to optimize for put in specialized optimized implementations of, like, for example, particular ops running on their architecture. So we want to keep encouraging that. I'm also hoping that there is some, it makes life easier if we can deal with a lot of the stuff like quantization and exporting from TensorFlow and get things boiled down to a TensorFlow Lite representation that's fairly easy for people to then take and run on their own devices without having to do, because what we see is a lot of the challenge for specialized hardware manufacturers is around building tooling around all of this export stuff. So does that sort of answer your question, or is that?
It's part of it, yeah.
Yeah.
Thank you.
Cool. Thank you.
All right, well, let's give Pete a round of applause. Thank you, Pete.
No, thank you so much.